average of the pretest. Okay, so this could be an interesting strategy, and preliminary simulation results show that it can be convenient to adopt this strategy. Okay, here is a sketch of the simulation study, which is in progress, so I can skip it. We started by simulating a situation like the one of Kim and Steiner, and obviously it is confirmed. We confirmed their analytical results. As for the case study on Invalsi tests, well, we have a huge data set about Italian students at the 5th grade and 8th grade. So it's a huge data set with more than 5,000 lower secondary schools. We consider Italian language test with binary items, so they are calibrated with Rush methodology. So as the outcome of the test, we simply take the total score and we normalize it to lie in the 0-100 interval. There are several covariates, and these are the estimates. This is a random intercept model. The first column is the conditional approach. The second column is the gain approach. And, well, the pretest is present in the conditional model and not in the gain, by definition. We added the school means of student level covariates, including the school mean of the pretest, also in the gain model, as I was discussing before. As for school level covariates, our interest is in private school, and we see that in the two approaches, the effect of private school is quite similar, okay? So it is interesting to know that school level covariates have very similar coefficients in the two approaches, contrary to student level covariates. But we should know that student level covariates are determined before the pretest, while school level covariates are determined after the pretest. Okay, so in the end, what are the findings? Well, the conditioning and gain score approaches yield very similar results in this application. Yeah, and Invalsi adopts the conditioning approach, but okay, we find that using the alternative gain model approach doesn't change much. This find is not reassuring per se, because the two approaches are likely to be similarly biased. The reasoning is that there's measurement error, so the conditioning approach has some bias. And so if the gain approach yields similar results, likely the common trend assumption is not strictly valid. So that's our reasoning. So we should investigate. So what's next? Okay, we have to perform a careful simulation study to evaluate bias and maybe also efficiency. For example, also to understand the role of the sample size, so number of clusters and cluster size, what is their effect on the results. We would like to extend the framework. For example, Kim and Steiner considered two complications. The pretest affects the treatment directly, and the pretest affects the final test. And in a multi-level setting, every issue has to be reconsidered, and also other issues. In particular, we would like to consider a range of models for the genesis of clusters. For example, clusters may be formed according to the ability, which is reasonable in many applications. So what happens in that case? Obviously, for applied researchers, it would be useful to have some diagnostic tools to decide between the two approaches. And another option is to try to go on with the conditional approach, trying to fix the measurement error issue with one of the available techniques to adjust for measurement error. So that's another option. So yeah, much work is needed. Okay.
Okay, so after this nice presentation about confounders, people want to, somebody want to ask a way question to Leonardo? Maybe later. Okay, so now we have the third presentation from Lu Yang from London School of Economics.
So, I think it's on the desktop.
Okay.
This one.
This one. Okay.
Okay, so I'm just
Scrivo un termo. No.
sorry.
Just 2 minutes. Okay. Task and
Oh, okay, great, thanks. Hi, my name is Yan Lu. This is a joint work with my supervisor, Irene and Yunxiao. So we propose a double mixture latent variable model for simultaneously detecting cheaters and also the leaked questions in standardized exams. So in the computer-based standard exams, usually sometimes the questions could be leaked before the exam. So a lot of maybe the test takers, they have prior access to these questions. They may read the questions, remember the questions. In that case, they have much higher probability to giving the correct answer to these leaked questions. So we define cheaters in this context as a test taker who may have seen the questions before the exams, and we define the compromised items by the leaked questions. So we have, in general, we have two research questions to answer. The first one is how we detect the test takers. So which test takers can be classified as cheaters, and how strong we can make the decision based on the evidence. And the second question is about how we detect the items. So we'll develop the double mixture model using two latent classifiers. So one classifier is for the test takers, and the other one for the items. And then we proposed a compound decision framework under the Bayes framework. We have the real data from a computer-based license test. So there are over 1,500 test takers, and there are 170 items in total. All the responses are binary, so either 0 or 1. The test company have already flagged 50 candidates as cheaters based on their internal database. And they also flagged 64 items as the items which are leaked. So the left panel is just the data, and the right panel is our aim. We want to detect this darker rectangular area, which means the item response probability to the questions, to the leaked questions, is much higher for cheaters than for non-cheaters. So our model based on the item response type model. So the simplest one is the Rush model. we use the rush model to characterize the normal item response behavior, which is for non-cheaters, their responses to non-leaked questions. So here the Y is for the data, and the theta I is the person-specific ability, and beta J is the item-specific difficulty level. So the proposed model adds another component, so which is including CI, which is the person-specific classifier. So if CI is 1, which means the test taker made cheated, and for the eta J is the item-specific classifier. For the eta J equals 1 means that item is leaked. So compare with the basic rush model, we add a component, and we use the delta to reflect the cheating effect. So if both eta I and eta J and CI equals 1, which means that the response probability for that person, for the cheater to the leaked questions is higher and increased by delta. And delta is strictly positive. So this one is a graphical representation for the model. So you got the data here, and the theta I, this is for all the person-specific parameters. They are assumed to be random, and delta J, including the beta J and theta J, they are for the items, and they are also random. So this is the first level parameter, and we assume the prior distributions for these two set of parameters, and the new 1 and new 2 are the parameters in the prior distributions. And the delta is the drift due to the cheating effect. It's a global drift, and we also assume the prior for the delta. So we estimate the model by using MCMC, and for the real data, it could be tricky about the starting points. So sometimes if we use the random starting point, they take very long to reach the convergence, or even doesn't reach convergence at all. So one solution is that we can use the joint MLE estimates as a starting point to initialize the MCMC. So after we got the posterior distribution for the random variable, latent variables, for Kc and for eta, we can calculate the posterior probabilities of eta being 1 and also Kc being 1. So we can have a rough idea for each individual and for each item, the chance of them being cheated or being leaked. So this decision based on single case. So if we made the decisions, for example, the D1 is 1, which means that test taker I is flagged as a cheater, and because maybe the posterior probability is above some threshold, omega. So sometimes people use 0.5 as a threshold and classify the people whose posterior probability above that level as cheaters. But that criteria is just individual based. So if we want to use all the information contained by all the people and all the items, we have to develop the compound decision framework. So for we separate this decision framework. So first one is for the people. For detecting the cheaters, the false positive, which means that you flag the innocent person as cheaters. So this one is a more serious problem or error than the false negative, which means the detection failed to flag the cheater. So we want to control that proportion. So in the table, which is the false false positive, the ratio of false positive over the total number of cheaters being detected. So we developed the local false discovery rate control. So the aim is to control the local false discovery rate, local FDR rate for person, and while try to minimize the local false non-discovery rate. So the local FDR basically is a posterior expectation of that ratio. So this formula defines the FDR for the person, and you can see the denominator based on the number of flagged people, and the numerator is like the sum of weighted, the weighted sum of the posterior probabilities. And this FDR is a non-decreasing function in the zeta, so we can try to find the optimum zeta. So the next part is we define the local false non-discovery rate. So this one we also need to minimize. This one has a, So this one is a posterior expectation of the false negative over all the number of innocent people as we detected. So the detection for cheaters now converted into the optimization problem. We need to control the local FDR rate to be as low as possible while minimize the local FNR rate. And because local FNR rate is an increasing function, and we can solve this zeta, which leads to an optimum solution. So the procedure for detecting the compromised item is quite similar to the detection of cheaters. The only slight difference is here because we want to we more care about the false negatives in this case than false positives, because we can try to flag as many compromised items as possible. If the items are not developed of the question not very expensive, the test company can just remove them with a new one. So here, because the false negative is of more concern than false positive, so we control the local FNR while minimize the local FDR. So it's another way around compared with the local FDR control for people. So that's the real data example. Based on the test company's information, there are only 2.8% test taker who cheated based on the test company's data, and this proportion is quite small. So it could involve some problems when we examined MCMC. The proportion for the compromised item is over 30%, so it's a good thing. So we assume some price distributions for all the random parameters or latent parameters in the model. So the first set is person-specific parameter. So theta, the ability parameter, normal, and Kasi is a Bernoulli random variable. And so we have two parameters in the price, and we need to further assume a hyper prior for these two variables. And the next set are the item-specific parameters. So the beta j, the difficulty level, normal distribution, and the eta j, Bernoulli, is the same, and we assume the independence between the classifier, latent classifier, and the item-specific difficulty level. And here we got 3 parameters in the prior distributions. So we further assume the hyperprior for the price in the first level. So the delta, the drift, which is a global parameter. So delta could be item-specific or person-specific. But in this data set, because the proportion of cheaters is quite small, so we worry about if this delta, we let delta to be item specific, it will be very difficult to maybe achieve the convergence because there are only quite a small number of people can provide that information. But if the proportion of cheaters is large enough, say over 5%, maybe we can let this parameter to be item specific, so we can see the cheating effect on each item. So here we assume the hyperprior for the proportion of cheaters and the proportion of leaked questions. We assume that just the uniform distribution because they are the proportions. And for the variances, we assume inverse gamma is a weakly informative prior, and also for the mean for the difficulty level. So this graph shows there are 2 box plots. So the left one is for the posterior probabilities of each test taker being cheaters. And the right one shows the posterior probabilities of each items being flagged as compromise item. So this is the decision making based on individual case. And we can see that for the horizontal axis means that the information provided by the test company, and we assume that that information is a true status, and we want to compare our discovery with their true status. So you can see for most test takers whose true status is non-cheater, they are also detected as non-cheaters. Only a few of them detected as cheaters. And for test takers identified by the test company as cheaters, the majority of them were also detected as cheaters. This can be reflected by the false negative rate. So the proportion of actual cheaters who are not detected is very low, is below 1%. And the first positive rate for the proportion of the innocent test taker who are detected as cheaters is 8%. And the right panel shows the posterior probabilities for the items. We only have 170 items, so this outlier is not very many. Also, the false negative rate for the individual-based decision-making for items is below 1%, and the false positive rate is 7%. So now we move on to the compound decision. In this case, we use all the information, including the test takers. So the horizontal axis is the number of test takers flagged by our decision-making procedure, and the vertical axis is the local FDR rate. So you can see when we specify the level at 10%, there are 22 people detected as cheaters, and at 5%, there are 41 people as cheaters, and when the level is quite small, there are 52. And this graph shows the compound decision making based on the FNR control for the item. They're at so the vertical axis is the local FNR rate, and the horizontal axis is the number of items flagged as compromised. So it's a decreasing curve, and at 10% level, there are 64 items detected as compromised, and at 5%, there are 72 questions detected compromised, and this one will be less conservative, and it will be over 100. So the test company provide information. The proportion is around 40% for the item detection. There are a lot of possible extension to the current model. So for example, in some computer-based standardized tests, we can get access to response times. So we can add another model to the current one, which characterizes the response time, follow a log-normal distribution. And so here we introduce another person-specific latent variable, the tau, which means the speediness for each person to complete the question, and alpha j is the mean response time for each item. And we also add some drift using the same similar pattern. So the gamma is also the positive one. So the drift means the cheating effect caused the reduction in response times on the log scale. So we can model the marginal dependence between response time and responses by assuming some dependence between ability, theta, and speediness factor, tau. So instead of assume a normal prior, we can further assume a multivariate normal prior. So this is a DAG for the model, including response time. So the original data responses, response time, and the first level we have ability, the classifier, and also the speediness. And for the items, we got difficulty, classifier, and also the mean response time spent on each questions. And we can, using the similar base framework, we add a hyperprior, and we also performed MCMC. We can use the same compound decision framework. So it could be very useful if in some data sets we have the response times, especially in most computer-based tests, they can provide such information. And also in our model, we assume that the cheaters can get access to all the leaked questions. But in practice, usually teacher can only get access a part of that leaked questions. So we may need to introduce another latent variable, another latent class for representing the different sources of leakage questions. Okay, that's it.
rimane qui? Quindi possiamo aprirlo anche in Italia?
Sì, sì.
Ok, se rimane qui, spero che nessuno la cancelli. Domani mattina me la prendo.
Ok, done.